Logistic regression. Logistic regression is used to analyze relationships between a dichotomous dependent variable or a binary dependent variable, a variable that has two groups, and continuous or categorical independent variables. When the dependent variable has two groups, that is, a binary dependent variable, then we call it binary logistic regression. If the dependent variable has more than two groups, for example, a variable that has very low birth weight, normal birth weight, so three groups ranging from 0 to 2, then we have multinomial or polycatomous logistic regression. Logistic regression combines the independent variables to estimate the probability that a particular event will occur. For instance, a subject will be a member of one of the groups defined by the dichotomous dependent variable if it's binary logistic regression. Therefore, in logistic regression, we predict membership or classification of cases into categories of the outcome variable based on a number of independent variables. Logistic regression is a classification technique. For a binary dependent variable, its two categories are denoted by 1 and 0, commonly referred to as success and failure. Models for binary data ordinarily assume a binomial distribution for the dependent variable. For a single independent variable, the simple model will be the probability that y assumes the value of 1 equals a plus bx or alpha plus beta x, which implies that the probability of success is a linear function of x. This is called the linear probability model. The logistic regression model is described by the formula of log the probability of y equals 1 over 1 minus the probability of y equals 1. The ratio of probability that y assumes the value of 1 over 1 minus the probability that y equals 1 equals the odds. For instance, when the probability of y equals 1 is 0.75, the odds are 0.75 over 0.25, which is equal to 3, meaning that a success is 3 times as likely as a failure. This formula uses the log of the odds, and we call it logistic transformation, or logit for short. The model can be abbreviated as logit probability of y equals 1, which equals alpha plus beta x, and we call it the logistic regression model. A statistical software uses natural logarithms in fitting the model, and therefore the previous formula can be expressed as the natural logarithm of p over 1 minus p, where p indicates the probability that y assumes 1, meaning the probability that y equals 1, for instance, 1 could stand for low birth weight, and the probability that y equals 0, 0 could be normal birth weight is 1 minus p. The natural log symbol refers to a natural logarithm, so if we know the regression, we could calculate the expected probability that y equals 1 for a given value of x, as is given below by the formula. The exp that you see in this formula stands for the exponent function, sometimes written as lowercase e. Natural logarithms and the exponent function The exp or the exponential function and the ln or natural logarithm are opposites. The exponential function involves the constant with the value of 2.72 approximately, and when we take the exponential function of a number, we take 2.72. So if we are looking to compute the exp of 3, or e to the third power equals 2.72 cubed, which equals 20.09. The natural logarithm is the opposite of the exponential function. If we take the natural logarithm of 20.09, we get the number 3. Although the goal here is not to really learn about exponential functions and natural logarithms, this is very helpful as we start the introduction here to logistic regression. So, because it's not easy to interpret the logistic regression coefficients as they are expressed in log odds, we use the exponential function to convert the coefficients into odds ratios. So the odds ratio is equal to exp of b, or e to the b power, where b is actually the regression coefficient. So if we take the exponent constant, which is 2.72, and raise it to the power of b, we get the odds ratio. For example, if the stated output indicates the regression slope as being 0.75, the odds ratio is approximately 2.12, because if we take the exponent exp of 2.72 to the 0.75 power equals 2.12. This means that the probability that y equals 1 is twice as likely as the value of x is increased 1 unit. Therefore, an odds ratio of 0.5 indicates that y equals 1 is half as likely as 0.5 or 0.5 times less likely. An odds ratio of 1 indicates that there is no association between x and y. So what is really the association between multiple linear regression and logistic regression? Both of those types of regressions are related, but they follow a different process in terms of how the coefficients are calculated. So in multiple linear regression, we predict the value of the dependent variable from several predictor variables. Here in logistic regression, we predict the probability of y occurring given known values of x. So the logistic regression bears many similarities to the linear regression. In the simplest form, when there is only one predictor variable x, the logistic regression equation from which the probability of y is predicted is given by the formula below, as you can see, the exponent there looks very familiar, very similar to the multiple linear regression. Despite this similarity between multiple linear regression and logistic regression, there is a good reason why we cannot apply linear regression directly to a situation in which the outcome variable is categorical. The reason is that the assumption of linear regression in logistic regression is violated. There is no linear relationship between a categorical outcome variable and an independent variable. And so to solve this problem, we transform the data into the logarithmic transformation. This transformation is a way of expressing a nonlinear relationship in a linear way. It expresses the relationship in logarithmic terms, and that's why we call it the logit. Now, let's take a look at the assumptions of the logistic regression model. Although logistic regression does not make any assumptions of normality, linearity, and homogeneity of variance, it does require independence of errors, which means that the cases of data should now be related. For example, you cannot measure the same people at different points in time. Multiple linearity can be an issue in logistic regression. Predictor variables, essentially your independent variables, should not be too highly correlated. As with multiple linear regression, collinearity or multicollinearity can be checked using the variance inflation factor statistics. This requires running a linear regression where you ignore all of the outputs related to the model fit and coefficients and simply check the VIF statistics, the variance inflation factor statistics, for the predictor variables. Overall, because it does not impose as many requirements, such as normality and linearity and so on, it is preferred to other similar methods, such as discriminant analysis. In terms of sample size requirements, the minimum number of cases per independent variable is 10, using a guideline provided by Hosmer and Lemichel, authors of Applied Logistic Regression, which is one of the main resources for logistic regression. Various statistical software exists for calculating the appropriate sample size, including Stata. There are three methods available for including variables in the regression equation or in a regression model. The simultaneous method, in which all independent variables are included at the same time. The hierarchical method, in which the most important variables we are interested in are entered in a specific sequence, followed by any control variables. And the stepwise method, in which variables are selected in the order in which they maximize the statistically significant contribution to the model. For all methods, the contribution to the model is measured by the chi-square test, which is a statistical measure of the fit between the dependent and independent variables, like the R-square we used in multiple linear regression. We know that in multiple regression, we use the least squares method to find the coefficients for the independent variables in the regression equation. For example, we compute the coefficients that minimize the residuals for all cases. Logistic regression uses the maximum likelihood estimation to compute the coefficients for the logistic regression equation. This method attempts to find coefficients that match the breakdown of cases on the dependent variable. The overall measure of how well the model fits is given by the likelihood value, which is similar to the residual or error sum of squares value for the multiple linear regression. A model that fits the data well will have a small likelihood value. A perfect model would have a likelihood value of 0. The maximum likelihood estimation is an interactive procedure that successively tries to get closer and closer to the correct answer. When Stata reports the iterations, it is telling us how many cycles it took to get the answer. The Stata output for logistic regression begins with an output for a model that contains no independent variables. It reports the initial log likelihood, which is iteration 0, which we can think of as a measure of the error associated trying to predict the dependent variable without using any information from the independent variables. So in this example, where we run a logistic regression on birth weight with the independent variables of marital status and prenatal care, we see that at iteration 0, the log likelihood is negative 284.35, while by the iteration 4, the log likelihood is negative 269.85. Although we don't usually request the iteration history because it does not usually yield us additional useful information, we may actually use this information to figure out if the model is better than an empty model. Basically, the model that we obtain is better than an empty model. In logistic regression, we predict the probability of an event occurring for a given person. For a given person, the y, the dependent variable, will be either 0, the outcome did not occur, or 1, the outcome did occur, and the predicted value of probability of y will be a value between 0 and 1. In multiple linear regression, we assess the model by explained versus unexplained variation, measured by the R-squared. In logistic regression, we use the log likelihood statistic, which is an indicator of how much unexplained information there is after the model has been fitted. Large values of log likelihood statistics indicate poorly fitting statistical models because the larger values of log likelihood are associated with more unexplained observations. The overall test of relationship between the independent variables and groups defined by the dependent is based on the reduction in the likelihood values for a model which does not contain any independent variables and the model that contains the independent variables. This difference in likelihood follows a chi-square distribution, and it is referred to as the model chi-square. The significance test for the model chi-square is our statistical evidence of the presence of a relationship between the dependent variable and the combination of the independent variable. In this example that we actually saw a little earlier, the value of the chi-square test is 29, and it is statistically significant, which means that the model fits the data. So this is a good model.